Okay, so now we're going to do a couple of examples. So if you remember, for hydrostatics, non-accelerating fluid, our equation for pressure was P2 minus P1 equals minus gamma Z2 minus Z1. Okay, whenever you write this equation, just be sure that if you do P2 minus P1 here, you also do Z2 minus Z1. Don't get those backwards or your sign will be mixed up. All right, so what we have here is we've got a scuba diver in a lake. Okay, so we're going to be able to use this equation, and what we're going to try to find is first an equation for pressure versus depth, which we almost have already, pressure at the bottom, and then a pressure change as it relates to the rate of ascent or descent. Okay, so one of the things we normally do make our lives easier is pick a coordinate system where z equals 0 at the free surface. You don't have to. You can pick z equals 0 anywhere, but it just makes our lives easier sometimes. So that's what I've done here. 1 is right there at the free surface in our coordinate system. Our z is going straight up from there. Okay, so for part A, let's just start with our hydrostatic equation, but we want an equation for any old pressure versus any old depth. Okay, so that would be our P2. Let's call P2 just P for this case. Just any P anywhere in there. That way it looks more like a variable. So P is minus P1 is equal to minus gamma Z minus Z1. All right, so this is what makes it easy as far as putting the coordinate system there at the free surface. Our Z1 now is 0. Okay, so we're practically there. Our equation then is P equals P1 minus gamma Z. That's our equation. We can plug in some constants. We know that that lake, doesn't say, but we assume that that lake has water, so our gamma, and actually what you want to do to find gamma usually is look in table 2.1 in your textbook, because that has, it's a nice table. It has a few gammas that you're going to use, most of the gammas that you're going to use in metric and in English. So I can't remember what page that's on, but right in the chapter, nice little table. So if you look in that, you'll find that gamma for water in metric is 9790 newtons per meter cubed. Okay, and P1 is going to be P atmosphere, because we're right there at the air interface for 1. So P1 equals P atmosphere. And we can either do P atmosphere 0 if we want to have our P engage, or P atmosphere is equal to 1 atmosphere, which is 101,350 pascals. So for gauge, P1 equals 0. For absolute, P1 equals 101.35 kilopascals. All right, and we can plug those two values, gamma and P1, in and get our equation. Let's just say that's done. Either one of those would be right on a test, as long as you indicate, this is going to be in gauge pressure. My final answer is in gauge or absolute. Okay, pressure at the bottom then. P bottom is P2. Okay, so we got an equation. P equals P1 minus gamma Z. Okay, just plug in 2's for your P's and your Z's. Okay, let's do gauge. 0 gauge. A lot of times it makes our lives a lot easier just to use gauge. So we can say then our P2 equals minus gamma Z2, and our Z2, looking at our coordinate system, is actually minus 100 meters. So be careful with your sign on this. Minus 100 meters. All right, so our answer here, plug in the 9790, multiply by 100, you're going to get 979 kilopascals. All right, so about 10 atmospheres. Goes up pretty fast in water because water is pretty heavy. All right, part C, this is the trickier part of it. So you're trying to find how P changes with the scuba diver going up or down. So what you're looking for is a rate. And a rate is a derivative with respect to time, right? So let's write this equation. So we had our P equals, and let's just leave it as P1 minus gamma Z. And let's find the rate. dP dt equals, well, we have to take, if we take the derivative of the left, we have to do the same with the right. ddt of P1 minus gamma Z. And so far I haven't plugged in a P1. It's going to be different, right, for gauge or absolute, but once you take the derivative, it's not going to be different because P1 is a constant. So ddt of P1 is actually 0. So it doesn't matter if you use gauge or absolute when you're talking about a derivative here. So what you're going to get is just minus gamma dz dt. Okay, so our rate of change of P is equal to minus gamma, our velocity of the diver. All right, if the diver's going up, pressure's going to go down. If the diver's going down, pressure's going to go up. All right, and this is important for the bends, basically. To try to avoid the bends, you want to avoid going up too fast because the pressure will drop too fast, and the nitrogen in your blood, you'll have excess nitrogen in your blood, it'll come out and bubble and be very painful. So it's important figuring this stuff out. All right, so we have our equation. We came up with that equation assuming that we had an incompressible fluid, so rho wasn't changing. Gases, what we do is something just a little bit different. Gases don't weigh much compared to liquids. So because of that, the change in elevation is actually not going to affect the pressure a whole lot unless you have a big elevation change. Okay, so what we normally do for gases, less than 200 meter elevation change, is just say that the pressure remains approximately constant. All right, so any gas up at the top of the room, bottom of the room, really we're going to just say, okay, that's at P atmosphere. Or if you're in a container that's pressurized, we're going to say the pressure is about the same all over that container if it's filled with a gas. If it's filled with a liquid, different story. The pressure is going to change with elevation. And just to illustrate this, if you go up 100 meters in air, you only get a pressure change of 1.2%. We saw it was 10 atmosphere change in water. All right, so you have everything you need really to do hydrostatic problems for liquids or for gases with the equation that we had, but that sign can be a little tricky. You know, you always got to remember to, if you put your z elevation at your free surface and you're going down, to remember the negative z and so forth. I find it a little easier just to use this alternate form, basically just to use delta z as always a positive, and then decide on the sign. And we always know what the sign is going to be because we always know that it's going to be a higher pressure below another value. So if you have one point below another point, that first point is going to be at a higher pressure. So you can always figure out what the sign should be to go in here. All right, so let's do an example using this. And this example is going to really carry over into the next lecture for next time when we do manometers. All right, so here we have a tank and it's got a couple of different liquids in it, plus it has gas. It has water, it has sludge with a specific gravity of 3, and it has air that's pressurized to 300 kilopascals. Doesn't tell us if that's gauge or absolute, so you know, we're going to assume that that's absolute. Okay, and you notice how the air doesn't say the pressure at this point is 300 and at this point it's something else, because since it's a gas, we're going to assume it's constant pressure throughout. When we get to the water, though, the pressure is not going to be the same. Okay, and for the sludge. Okay, so what we want to do, let's assume it's all incompressible and P air equals constant. How about that? All right, so I have a method here that's going to work for your manometer problems as well as for this problem. Whenever you have multiple fluids in there, there's a nice, easy way to use this equation. First thing you want to do, so let's write down a method here. First thing you want to do is just label all your interfaces between different fluids. Let's call this 1, this 2, and everywhere also where you're trying to find something. So pressure at the bottom of the tank, trying to find 3. So label interfaces and finds. Okay. If they're not already labeled, label all your delta z's. And sometimes you'll just make a variable if you don't know what that is. That might be what you're solving for. Okay, for each section. Here we don't have to do that because we already have 100 meters and 50 meters already written down. And then the third thing you want to do is write your hydrostatic equation for each fluid. For each liquid, really. All right, so let's go. You can either, oops. How did I do that? All right, sorry. You can either start at the bottom or start at the top. It's up to you. Same difference. I'm going to start at the top. So I'm going to write P1 minus P2. And that's from our equation. What I'm doing is writing from our equation right here. P2 minus P1. This time I did 1 minus 2. Rho g is gamma. Let's rewrite that. Gamma delta z. And what I'll do is just leave out the sign until I figure out what it should be. Okay. Equals gamma. And the gamma we're talking about, 1 to 2, is water. And our delta z is 100 meters. Okay, and then what I need to do is figure out what is that sign. Okay, P1 minus P2, well, 1 is above 2. Okay, so 1 is going to have a lower pressure than 2. 2 is going to have a high pressure because it's deeper, right? So that means P1 minus P2 is negative. So I want to put a negative sign. Let's write the next equation for the sludge. P2 minus P3 equals gamma sludge times 50 meters. Okay, now let's figure out the sign. Well, 3 is going to have a higher pressure than 2, also a negative sign. Okay, now that we have this, well, before we do that, let's figure out that gamma sludge. We have gamma sludge, and up here it says Sg equals 3. Well, if you remember Sg, that was rho of the sludge, and since that's a liquid, over rho of water. And that also means that that 3 is equal to gamma of the sludge over gamma water. All right, so we can rewrite that gamma sludge as 3 gamma water, and then times that 50 meters. All right, next thing to do is take those two equations and add them together. And the good thing about this, all of your intermediate pressures are going to cancel out. And what you get is P1 minus P3. And you need to add these two together. Let's add this one and this one. And you're going to get, oh, I should have a minus in here, minus gamma water times 100 meters plus 3 times 50 meters. All right. And from there, I can just go ahead and solve. I know P1 is 300 kilopascals. And if I go ahead and solve, I'm going to get P3 equals 2.75 megapascals. Okay. And if that 300 kilopascals was absolute, then this is also absolute. If it was gauged, then this was also gauged. All right, so that's it. So go ahead and finish your quiz, and I'll see you in class.